All right, hey guys. So we finished organic chemistry and now we are on to equilibrium, which is a really cool unit because we're looking at reactions that occur in both directions. Okay. So in this first example, example one, all I've done currently on the whiteboard is write out the ice table and the graph like you guys have in your notes. Now I just want to take us through the ice table because developing ice tables is something that we're going to be doing for the entire unit. So what I've done is I've just written out the chemical reaction above and I've kind of sectioned it, all right, so that there's a column for each chemical. There's a column for H2, a column for I2, and a column for HI. This drawn out, colored in area is just nothing. We don't use it, so I've just kind of colored it in. Now over here, when we have an ice table, the I, the C, and the E stand for three different things. I stands for the initial concentration of the chemicals. That's why we have square brackets. C stands for the change in concentration of the chemicals, and E stands for the equilibrium concentration once equilibrium is established. So what we're going to do is we're going to calculate those, and then we're going to plot them on the graph so we can see it visually. So in this question, we started with 1 mole of hydrogen and 1 mole of iodine in a 1 liter container. So all I've done is take 1 mole divided by 1 liter to get my concentration. Now, the question is going to become, at the end of the day, we always are trying to find equilibrium concentrations. So I'm looking for these two values. But in order to go from the initial to the equilibrium, I have to go through the change. In other words, I need to figure out what is changing. In order to figure out what is changing, you have to look at the column that has two entries. So I can't look at hydrogen because it doesn't tell me what it ends up at. I can't look at hydrogen iodide, but I can look at iodine. Now, if I look at iodine, I start at 1 mole per liter, okay? And I go down to 0.220 moles per liter. So I've started at 1 and I've decreased my number to 0.220. That means that the change in concentration was negative, okay? So this iodine has lost some of its chemical compound, okay? Now, because the coefficient is 1, we don't know what that change is yet. So we're just going to give it the value of x. So we're going to say that it started at 1, it lost something, and it ended up at 0.220, okay? Now, let's look at how this affects hydrogen, okay? Think about the left side and the right side. If this reactant has lost some, it's reacted, what do you think is going to happen to hydrogen? Well, if this reactant is being used up, is being lost, chances are this reactant will also be used up, okay? So what can I take away from that? If the left side is negative, the right side will be the opposite. I cannot have one reactant being used up and one reactant being produced. That just logically does not make sense, okay? Another way to think about it, guys, is if we knew that this reactant was being reduced, in other words, it was reacting to produce something, well, let's think about it. Initially, I had absolutely no product, none. But if this is being reacted, that means I'm producing my product. So I'm going to put a plus sign on the change. Now I'm going to give it the value of x, but there's a little difference here. Each of these had a coefficient of 1, so we just put 1x. Here, we are producing twice the amount of hydrogen iodide, so I have to say I'm adding twice the amount of change, okay? So now what I need to do is I've established my ice table, I've identified the initial concentrations and the changes. Now what I need to do is figure out what that change is. And to do that, I'm going to look at iodine. So what does this mean? So what this means, guys, is I initially started at 1 mole per liter. I lost some amount in X, and I ended up at 0.220 moles per liter. Now, you are all mathematicians. Okay, most of you are in 30-1, 30-2. You know how to do math. This is a very simple equation. all you need to do is rearrange and solve for x. So I'm going to bring the x over here. I'm going to bring this over here. I'm going to get 1 mole per liter minus 0.220 moles per liter is x. So 1 minus 0.220 is 0.78. Again, if we're subtracting, this has 3 decimal places, this has 2. So our final answer has to have as few as possible. So 0.78 moles per liter is the change in concentration. Now, we've established that. So what that means, guys, is if I know that 0.78 is x, I can sub that in here. 1 minus 0.78, well, 0.220. I can also sub it in here. 0 plus 2 times 0.78, so 2 times 0.78 plus 0, because that's the initial concentration, is 1.56 moles per liter. Okay, so all we've done right now, ladies and gentlemen, is we have written the initial concentrations, said, okay, if this concentration is going down, that means the reactants are being used up. They are producing products. Makes sense because I had nothing, so I can only produce it, and I end up with these numbers. So all I'm going to do is just put, just so we can finalize them, I'm just going to put a little box or bubble around them just so we can see them. These are our equilibrium concentrations. So this reaction is going back and forth, back and forth, back and forth. And once it reaches equilibrium, the concentration of these chemicals will be as such. Now the question is how am I going to put those on a graph? Okay. So we only graph equilibrium concentrations. Okay. Let's give hydrogen green at 0. So initially it was at 1. So let's say, let's go 1 here. Okay. And let's go 2 up here. Okay. So that means this is about 0.5 and this is about 1.5 moles per liter. Okay. Initially, the concentration of HI was 1. Or sorry, H2. So all I'm going to do is just, it was 1, it was happy, it was having a good time. Okay, I'm just going to draw a straight line. Now, when it changed, it went down. Okay, and it went down and ended up at 0.220, which is, let's say, somewhere down here. So it ended up here, but to get there, it went down. So I draw a little curve, not a straight line, because it's not linear. Probably did this over time. All right. I'm going to draw a little curve, and I'm going to end up at 0.220, right around there. Okay. Might not be exact, but I just want you guys to see what I'm doing. Okay. So I'm going to, that's for H2, so I'll write that in green. Okay. Well, now let's take a look at I2. Now, in this case, I2 has the exact same trajectory. I2 starts at 1. I'm just going to draw it in color underneath so you guys can see it, but in reality, it would be on top of each other. It started at 1, and then it went down, again curved, because it's not linear, and it ended up at 0.220. So both of these reactants had the same outcome. They were strolling along happy at 1, but then the system changed because it wanted to reach equilibrium, and it ended up at 0.220. Now, what happened to the product? Well, if the reactants went down, chances are the product goes up. And we see that. We see iodine go down, we see hydrogen go down, we see iodine increase. Iodine started at 0. So I'm going to draw a straight line at 0. Okay. And it ended up at 1.56, which is, let's just say right around there. Oops, that's not a very straight line. Nope, still not straight. Come on. There we go. Well, it's not going to be a straight line. It's going to be some sort of curve. Okay, so we started at 0 and we ended up at 1.56, and I'm going to put HI there. So what you guys can see is that initially we had these two concentrations, but after equilibrium was established, we have these stable concentrations. Okay, these concentrations will not change at equilibrium. Okay, and that's all I really wanted you guys to see. So make sure that as you're going through your notes, you fill in this ice table, you draw the graph. I would recommend using some different colors so you guys can see that. But the skills that I want you guys to take away from these examples are developing the ice tables, solving for that change variable, and then showing it visually on a graph.